There's a particular kind of quiet that comes when you stop trying to sleep and just let the ceiling be a ceiling. Not a metaphor, not a surface for projecting anxious thoughts about tomorrow. Just plaster or paint or whatever it is, just a thing that exists above you while you exist below it. And somewhere in that stillness, if you've been here before in this kind of late night nothing, a thought sometimes arrives that doesn't feel like the other thoughts. Not urgent, not about anything on a list. It arrives the way certain questions arrive, sideways and a little too large. What was there before the beginning? Most people remember asking something like this, not necessarily in those words. Maybe it was, "But what was before that?" said to a parent who was trying to explain where the universe came from, or where time came from, or why there is anything at all. And the parent either said something that felt vaguely satisfying in the moment and didn't hold up later, or they paused in a way that told you everything. That pause being its own kind of answer. The question got set aside. Life accumulated. You learned what a mortgage was, what a deadline felt like, what kind of tired you get from not sleeping enough for 4 years in a row. But the question didn't go anywhere. It's still sitting there, in the same place you left it. I want to spend some time with it tonight, before we get to physics, before we get to anything that involves a physicist's name or a year or a journal paper, because I think this question deserves a moment of just being a question, not a puzzle to be solved, not a gap in our knowledge waiting to be filled in, just a question. The kind that has a strange weight to it when you actually hold it. This channel is self-funded. If you've found something here that helps you sleep or helps the world feel a little more like a place worth being curious about, there's a link to the Patreon in the description. It keeps this going. No pressure, genuinely none. But it matters more than I usually say. So, before the beginning, here's what makes this question different from most. Most questions, when you pull on them, lead somewhere. Why is the sky blue leads to light scattering? Why do we dream leads to neuroscience and then to more questions? Sure. But each new question is at least a different question, a step in some direction. There's a thread, and the thread goes somewhere. This one doesn't. When you ask what came before the Big Bang, the thread doesn't lead somewhere. It leads back. You follow it and find yourself holding the same question again, dressed slightly differently. What started the thing that caused the Big Bang? What was the state of whatever existed before that? And before that? The thread doesn't unravel toward an answer. It unravels the floor you are standing on. That's not an accident. That's the question's actual structure. Children notice this instinctively, which is, I think, one of the genuinely interesting things about children. Not because they're wiser, not that, but because they haven't yet learned which questions are allowed to stay open and which ones are supposed to get quietly retired. A child will sit with "but what was there before?" and feel its weight without immediately reaching for a way out of the discomfort. Adults, most of the time, have trained themselves to swap that discomfort for something more manageable. We don't know yet. Science is working on it. Have some dinner. And to be fair, that's not wrong. Science is working on it. Genuinely working on it with some of the most rigorous and strange and quietly beautiful thinking humans have managed to produce. But, and this is the part I find myself returning to, even the most sophisticated answers physics has offered so far don't quite kill the question. They redirect it. They dissolve it in some frameworks and reopen it in others. And in a few cases, they suggest something even more disorienting, that the question might not be broken because we lack information, but because the question itself is asking about something that doesn't exist. Not, We don't know what was there before, but there may be no before to ask about. Sit with that for a second. Actually sit with it, don't rush past it. I was on a walk once, late evening, one of those walks you take when a room has gotten too small. I wasn't thinking about physics. I was thinking about something mundane, something at work, I think, or something I'd said that I wished I hadn't, the specific low-grade hum of mild social regret. And for no reason I can identify, the question just surfaced. What was before the Big Bang? And what hit me wasn't the usual intellectual curiosity. It was something more like vertigo. Standing on a pavement with the smell of someone's dinner drifting out of a window somewhere nearby, and feeling the bottom of the question open up. Because the question doesn't just point outward, into deep space and deep time, it points at time itself, at the thing we use to make sense of before and after, of causes and effects, of stories with beginnings. And if time had a beginning, if time is a thing that started, then asking what came before it is like asking what's north of the northernmost point. The grammar works, the meaning doesn't. Or maybe it does, and we just don't have the language for it yet. That's possible too. This is the self-correction I keep having to make when I think about this stuff. I start confident that the question is malformed, that physics has shown us the exit, and then I pull back a little, because I'm not sure malformed is right. The question feels malformed from inside the universe, using tools made of time. What those tools miss might be the whole point. There's a type of question in physics, not common, but appears a few times across the history of the field, where asking it carefully enough changes what you thought you were asking. You start with what is the speed of light relative to the ether, and end up learning that the ether isn't there. You start with what is the precise position and momentum of this particle, and end up learning that precision itself is bounded. The question doesn't just lack an answer, the question had a hidden assumption baked into it, and finding that assumption is the discovery. What was before the Big Bang may be that kind of question. The hidden assumption is time. The assumption that time is a container, something pre-existing and infinite, inside which events, including the beginning of the universe, occur. On that assumption, of course something was before the bang. Time was before it. Empty time maybe, but time. But general relativity, and this was one of the things Einstein's equations made genuinely inescapable, treats time not as a container, but as a fabric, woven with space, stretchable, warpable, capable of beginning. If space-time itself was born in or with the Big Bang, then there is no temporal container pre-existing the event. There's no clock that was already running before the universe switched on. The question, what was there before, assumes a before that the physics doesn't supply, and yet the question doesn't go away. Even knowing this, even holding the logic of it, the feeling persists, that there must have been something, that nothing is not a stable answer. That ex nihilo, truly from nothing, is more unsettling than any elaborate pre-bang cosmology could ever be. That feeling is not nothing either. It might be pointing at something real. What we'll spend time with across the next few hours is the collection of ideas physicists have actually proposed, not guessed at, not dreamed up loosely, but built with mathematics and internal consistency and tested against what the sky tells us. Some of them say the question is unanswerable in principle. Some say there was no before. Some say there was a before, and it looked nothing like what followed. One of them says the universe before the Big Bang was, in a specific technical sense, a mirror image of ours, running in reverse, made of antimatter, the whole thing. None of them are simple. All of them are strange. But before any of that, before the names and the frameworks and the theorems, it seemed right to spend a little time just here, with the question in its raw form, the version a child asks, the version that surfaces late at night when the ceiling's just a ceiling and you're not trying to sleep and the room is quiet. What was there before? It's a good question. It might be the best question, not because we've answered it, we haven't, not really, but because of what happens when you take it seriously, because of where it goes, and it goes somewhere genuinely strange. Run it backwards. That's the instruction. That's all it takes to start. Take the universe as it is right now, galaxies spread across hundreds of millions of light years, still moving apart, still thinning, the distances between things quietly growing, and reverse it. Not as a thought experiment dressed up in metaphor, as a mathematical operation, an actual reversal of the observed expansion. What you get is compression, slow at first, or rather slow in terms of what changes visibly. A few 100 million years of reversal and the galaxies are merely closer. Still distinct, still separated by gulfs that would take light millions of years to cross. You wouldn't notice much difference if you were somehow watching. The universe would look dense, younger feeling, but not yet strange. Keep going. 1 billion years back, 2 billion, 5, the cosmic web, that vast scaffolding of filaments and voids that large-scale structure forms, starts to flatten into something less organized. The great clusters of galaxies pull inwards toward each other. The voids shrink. There's a faint smell of something burning coming through the window from a neighbor's yard, and I'm aware of sitting at a desk, very late, trying to think clearly about compression at cosmological scales, which is fine. It's a strange thing to do at this hour, but here we are. 8 billion years back, the universe is roughly half its current size, not half its mass, not half its matter. All of that is still there. But the volume has halved. Everything packed into half the space. The density has gone up. The temperature has gone up. These two things travel together. Squeeze at a gas and it heats. The universe, running in reverse, is being squeezed. What's important here, and this is the part I want to stay on for a moment, is that this isn't science fiction. This is what the equations of general relativity actually say when you apply them to an expanding universe and run the clock backward. The expansion we observe today is not mysterious. Galaxies aren't flying apart because something pushed them. Space itself is stretching. The distance between things is growing because the fabric they're embedded in is growing. And if that fabric is growing now, then earlier it was smaller. There's no assumption needed beyond what we can measure. 11 billion years back. The universe is a fraction of its current volume. The first stars are forming, or rather unforming, in reverse. Matter that has organized itself into stars and galaxies begins to unorganize. The structures dissolve. What remains is a hot, dense plasma. Protons and electrons moving too fast to bind into atoms. Light can't travel freely through this. The plasma is opaque, constantly absorbing and re-emitting photons. The universe is a wall of bright fog. This fog has a name, the photon epoch, and the edge of it. The moment the universe cooled enough for electrons to bind to protons and form neutral hydrogen is the farthest back we can see with light. Everything before that point is hidden, not hidden in a metaphorical sense, hidden because before that moment the universe wasn't transparent. Any photon trying to travel from further back gets absorbed almost immediately. We have a photograph of that fog surface. We call it the cosmic microwave background. It's the oldest light we'll ever see with any kind of electromagnetic detector. Uniform in almost every direction. Slightly, almost undetectably, and not uniform, with temperature fluctuations of about 1 part in 100,000. Those fluctuations are seeds. They're the places where gravity had just a little more to work with, where matter would eventually clump into the first structures. But the photograph is a wall, not a window. Keep reversing, past the photon epoch, past recombination, into the first minutes, the first seconds. The temperature is rising steeply now. At 3 minutes back from the beginning, protons and neutrons are just barely fusing into the first atomic nuclei. Helium, a little lithium, deuterium. This is nucleosynthesis. The proportions of these elements in the universe today match with uncomfortable precision what the equations predict for a universe that passed through a hot, dense state roughly 13.8 billion years ago. That match is not nothing. It's one of the reasons the Big Bang model isn't just a story. It's a prediction that came true at 1 second back. The universe is 1 billion degrees. Neutrinos, which barely interact with anything, or decouple from the rest of matter and begin streaming freely. They're still out there, those neutrinos, a background sea of nearly massless particles crossing the universe in every direction. We haven't directly detected the cosmic neutrino background the way we've detected the microwave background, but the physics says it's there. The math is consistent. At 1/10,000th of a second, quarks haven't yet bound into protons and neutrons. The universe is a quark-gluon plasma. This is a phase of matter that physicists have actually recreated briefly at the Large Hadron Collider by smashing heavy nuclei together at close to the speed of light. The resulting fireball lasts for an unimaginably short duration, and then the quarks bind back up. But in that brief hot mess, which is the wrong phrase technically, but it's what it looks like, the early universe is being approximated. Not perfectly, but approximately. So, go further. Here's where the language starts bending. At around 10 to the negative 36 seconds, a number so small that writing it out in full would be mostly zeros, the universe is thought to have undergone a period of exponential expansion. Inflation. In a fraction of a second, the observable universe inflated from something smaller than an atom to something roughly the size of a grapefruit. This is the mechanism physicists use to explain the flatness of the universe, its large-scale uniformity, and the specific statistical pattern of those temperature fluctuations in the microwave background. Whether inflation actually happened, and in what precise form, is still being worked out. The Planck satellite and other CMB observations have put constraints on inflationary models. Some versions have been ruled out, others remain viable. It's not a settled science in the way that nucleosynthesis is settled. It's a well-motivated framework with strong circumstantial support and some genuine unresolved problems. But even inflation, even if you accept it, doesn't answer the question we were moving toward. Inflation describes what the universe did at an extremely early time. It doesn't describe what preceded the conditions that made inflation possible, or why the inflaton field, the hypothetical field driving that expansion, had the energy it had or where that energy came from. It pushes the question back, but it doesn't dissolve it. Now we're approaching something genuinely different. At 10 to the negative 43 seconds, the Planck time, general relativity stops working. Not fails as in gives wrong numbers. Stops as in the equations themselves become undefined. The density of the universe at this point is so extreme that quantum effects and gravitational effects are both significant simultaneously, and we have no theory that handles both at once. General relativity is a theory of smooth curve spacetime. Quantum mechanics is a theory of discrete probabilistic interactions. In normal conditions, you can use one or the other depending on scale, but at the Planck scale you can't separate them. Both matter, and they are incompatible. What the universe was doing in that final sliver before the Planck time we genuinely don't know. Not in the way we don't know yet, maybe in a more permanent sense, maybe not. There are candidates, loop quantum gravity, string cosmology, others. They make different predictions about what happens at and before the Planck time, and some of them have observable consequences that future experiments might test. But right now, the honest statement is, the reversal of the expansion, which was clean and well-defined all the way back to a fraction of a second, becomes undefined at a specific point. Not because the math is hard, because the math we saw was not built for this regime. And just past that point, or rather, just before it going further backward, is where the question what was there before the Big Bang starts to mean something different than it did when we first asked it. Not more mysterious exactly, more specific, more technically strange. The question isn't what was in the empty space before the universe. Asking it that way assumes the empty space was already there. The question is whether time and space themselves had a beginning, and if they did, what that even means for a word like before. That's where we're going. Light from the sun takes 8 minutes to reach you. You've probably heard that. It's one of those facts that gets cited often enough that it stops landing. 8 minutes, fine. The sun is far. Light from the next nearest star takes 4 years. From the Andromeda galaxy, which is visible to the naked eye on a clear night, a faint smear in the direction of the constellation that shares its name, light takes 2.5 million years. 2.5 million years of travelling at the fastest speed anything in the universe can travel, and it arrives at your eye on a Tuesday. The observable universe is about 93 billion light years across. Not 13.8 billion, that's the age, and the universe has expanded while its light was travelling, which is why the numbers don't match and why cosmological distances require their own careful vocabulary to avoid confusion. 13.8 billion years is the age. The time elapsed since the conditions we call the Big Bang. Try for a moment to actually hold that number, not to understand it conceptually. You can't, not really, no one can, but to feel its weight, the way you feel the weight of a stone before you understand its geology. 13.8 billion years. A billion seconds is about 31 years. A billion minutes is roughly 1,900 years, which means a billion minutes ago, Rome was still an empire. A billion hours ago, anatomically modern humans didn't exist yet. We were something earlier, something that would eventually become us, but wasn't quite. A billion years ago, the most complex life on Earth was microbial. 13.8 billion years is not just old. It's a duration so vast that it makes the entire history of complex life on this planet. The Cambrian, the dinosaurs, the ice ages, everything to look like a rounding error, a thin skin on a very long number. The universe is almost incomprehensibly older than nothing that has ever thought about it. And yet, when we reverse the expansion all the way back, through all those billions of years, through the formation of galaxies and stars and the first atomic nuclei, we don't arrive at something eternal. We arrive at an edge, a place where the backward journey stops being a journey and becomes something else. What's strange about the edge, the thing I keep returning to when I sit with this number, is not that it's large, it's that it's finite. That 13.8 billion is not a placeholder for infinity. It is a specific number, a measured number, arrived at through multiple independent methods that have converged over decades of increasingly precise observation on approximately the same answer. The universe has an age, which means it had a beginning, or something that functions like a beginning, or something that our word beginning points toward without quite reaching. That's the corridor, Long, yes, almost insultingly long given how briefly anything capable of measuring it has existed. But corridors by definition have two ends. We've been standing in the middle looking back. The far end is where we're headed. The word has done too much work for too long. Singularity. It sounds like it names something. A place, a moment, a seed, the dense hot point from which everything erupted. And in the popular telling of the Big Bang, that's more or less what it is. The singularity, the origin, the thing before which there was nothing and after which there was everything. It gets described in documentaries with a kind of reverence, this word, usually over footage of CGI fireballs expanding outward. The singularity. The beginning. But here's what it actually is, technically. A location in the equations where the output becomes infinite. That's it. That's the whole thing. A singularity is what mathematicians call a point where a function breaks down, where you're dividing by zero essentially, where the answer stops being a number and becomes undefined. When physicists say the Big Bang emerged from a singularity, what they mean, precisely, is that when you run the equations of general relativity backward to a certain point, the numbers stop making sense. Density goes to infinity, temperature goes to infinity, the curvature of space-time goes to infinity. Infinity, in physics, is almost never the answer. It's almost always a signal. It's a signal that the theory has been pushed outside the range it was built for. General relativity is extraordinarily good at describing gravity across an enormous range of scales, from the precession of Mercury's orbit to the merging of black holes a billion light-years away. It has been tested, and it has held. But it was built, like all physical theories, with certain assumptions embedded in it. One of those assumptions is that space-time is smooth and continuous, a fabric that can be curved and stretched, but not, fundamentally, as granular. Not made of discrete units the way matter is made of atoms. Quantum mechanics, on the other hand, is built on discreteness, on the idea that energy comes in chunks, that transitions are probabilistic rather than deterministic, that the very act of measurement has physical consequences. It is also extraordinarily good, arguably the most precisely tested theory in the history of science. And at normal scales, at the scales where galaxies form and stars burn and people exist, general relativity and quantum mechanics don't conflict because they operate in different regimes. You use one for big heavy things, you use the other for small light things. At the Big Bang singularity, you need both at once, and they don't work together. We don't have the theory that unifies them, not completely, not in a form that makes clean predictions about the Planck scale universe. String theory is a candidate. Loop quantum gravity is a candidate. Others exist. None of them are finished in the way that general relativity and quantum mechanics are finished. So, what the singularity actually represents is the edge of the map, not the edge of the territory. I've been thinking about this. Maybe this is a strange way to put it, but the singularity has functioned for decades as a kind of emotional punctuation mark in the story of cosmology. It gives the story a beginning, a crisp, unambiguous start, and human minds, which are deeply, almost compulsively narrative, find that satisfying. There was nothing, then there was a singularity, then there was a universe, clean, ordered, causal. The problem is that the physics doesn't actually say there was nothing before the singularity. The physics says something more uncomfortable. At the singularity, the physics stops. Full stop. General relativity cannot describe that point, or what precedes it. The model breaks, extrapolating backward through the singularity and saying, and before this nothing existed, is not a conclusion the equations support. It's a story we added, a reasonable story maybe, an intuitive one certainly, but added nonetheless. This is the understated contradiction that sits at the heart of how the Big Bang gets communicated. We say the bang was the beginning, but the theory that predicts the bang can't actually describe the bang itself, let alone what, if anything, preceded it. The moment everyone points to as the origin is precisely the moment the theory goes dark. There's something almost funny about that in a dry sort of way. The most famous event in cosmic history is the one we understand least. Now, here's where it gets more specific and more interesting. The Penrose-Hawking singularity theorems, developed in the 1960s and early 1970s, Hawking's doctoral work feeding directly into this, proved that under the assumptions of general relativity and reasonable energy conditions, singularities are not accidents or edge cases, they're inevitable. Any universe that is expanding today must, if you trace it backward using only classical general relativity, have originated in a singularity. It's not a quirk of the math, it's a theorem, a proof, which sounds on the surface like strong evidence for a beginning. And it is, within classical general relativity. But those theorems carry their assumptions with them, and one of the critical assumptions is that the energy conditions hold all the way back. Quantum effects at the densities near the Planck scale can violate those energy conditions. Quantum pressure in certain frameworks can become repulsive in ways classical matter cannot. And if the energy conditions fail, the singularity theorems don't apply. This is not a loophole in a legal sense. It's a genuine physical question. Do the energy conditions hold at Planck densities? Classical GR says yes by assumption. Quantum gravity says possibly not. This is one of the places where the two frameworks directly conflict and where the answer actually matters for whether the universe had a hard beginning or something softer, something that might have a before. There's a specific number worth sitting with here. The Planck density, the density at which quantum gravitational effects become dominant, is approximately 10 to the power of 96 kilograms per cubic meter. That is not a typo. The density of water is 1,000 kilograms per cubic meter. The density of a neutron star, already so dense that a teaspoon would weigh 1 billion tons, is around 10 to the 17th. The Planck density is 10 to the 96th. It is so far beyond any density that occurs anywhere in the observable universe today that the words we use for dense stop carrying meaning. At that density, space-time itself, according to most candidate theories of quantum gravity, stops being smooth. The continuous fabric of general relativity becomes something else, discrete, quantized, a kind of stuff that doesn't have the same properties as the space-time we can describe with Einstein's equations. And if space-time becomes something else at that density, then the question what happened at the singularity might be grammatically similar to asking, what is the colour of jealousy? Not unanswered. Malformed. The singularity in this reading is not a moment of creation. It's a symptom of applying a continuous theory to a regime where continuity doesn't hold. Like trying to describe water as a smooth fluid at the scale of individual molecules, it works, until suddenly it doesn't, and the breakdown mode isn't telling you something about a mystery in the water. It's telling you that you've hit the limit of the smooth fluid approximation. None of this means the universe didn't begin. It might have. Several serious frameworks suggest it did. Began in a specific technical sense, from a condition that was not preceded by time in any conventional meaning of the word. We'll get to those. But it does mean that the singularity, the word, the concept, the CGI fireball, spabora, should be held more loosely than popular science has tended to hold it. It is not a thing, it never was. It is a boundary condition on theory, a flag planted at the edge of what that theory can handle, And what lies beyond that flag is not described by the theory that planted it. The math gave up. That's the honest description. What comes next, in the physics and in this, is what various people have proposed lies on the other side of that giving up. Some of those proposals are elegant. One of them involves imaginary time, which sounds like a poet's invention and turns out to be rigorous mathematics. Another involves the universe bouncing rather than beginning. Another involves a mirror image of everything we know running in reverse on the other side of a bang that is not quite a beginning. The singularity was a placeholder. Something always was going to replace it. There is a specific kind of relief that arrives when a very complicated problem turns out to have a very simple structure underneath it. Not a simple answer. The answer can still be strange, still be hard to hold, but a simple shape. A geometry you can almost feel with your hands, even if what it describes is the origin of time itself. Stephen Hawking found that shape in 1983, working with the physicist James Hartle, and the shape was a shuttlecock, or something like one, a badminton shuttlecock, that small, feathered, slightly absurd object whose bottom comes to a smooth, rounded point rather than a sharp one. And that rounding, that gentle curve at the base, is what the proposal is actually about. Not the shape itself, obviously, what the shape represents. But let's not rush there, let's come at it the way Hawking and Hartle came to it. Which is from behind, which is from the direction of a problem that had been sitting in the middle of cosmology for years, like something no one quite wanted to trip over. The problem was boundary conditions. In physics, when you want to describe how a system evolves, how it moves, how it changes, you need two things. You need the equations of motion, the rules that govern how the system changes from one moment to the next. And you need the initial conditions, the state of the system at some starting point, from which the equations then carry it forward. The equations are often beautiful, often universal. The initial conditions are, in a sense, arbitrary. They are what you have to specify from outside the theory. They are the given. For the universe, this is a problem with nowhere comfortable to stand. What are the initial conditions of the universe? What was the state of everything at the very beginning, from which the equations of general relativity and quantum mechanics then evolved everything we see? You can't observe the initial conditions directly. The early universe is hidden behind the photon fog of the microwave background. And whatever came before the Planck time is beyond the reach of any theory we have fully in hand. So you either assume something about the beginning, which feels like cheating, or you try to derive the initial conditions from some deeper principle, which is what Hartle and Hawking actually attempted. Their proposal was, in Hawking's own description, that the boundary condition of the universe is that it has no boundary. Sit with that sentence for a moment, because it earns the sitting. The boundary condition is that there is no boundary. The initial condition is that there is no initial condition, or rather, that the question of initial conditions dissolves when you look at it from the right angle. To understand why that isn't just word games, you need to spend a moment with something called imaginary time, which I know sounds like a thing someone invented to avoid answering a question. It isn't. It's a mathematical technique, specifically a rotation in the complex plane called a Wick rotation after the physicist Giancarlo Wick, and it's been used across quantum field theory for decades. It is not exotic. But what Hawking and Hartle did with it in the context of cosmology is genuinely unusual. In ordinary physics, time and space behave differently. There are both dimensions, yes, but time has a different sign in the equations. It enters with a minus where space enters with a plus, which is what gives space-time its particular geometry, its causal structure, its distinction between past and future. You can move freely through space in any direction. You cannot move freely through time. The asymmetry is real, and it is baked into the mathematics. But imaginary time, time multiplied by the square root of -1, which is what a Wick rotation does, removes that asymmetry. In imaginary time, all 4 dimensions of spacetime behave the same way. Time becomes mathematically indistinguishable from a spatial direction. The distinction between past and future, between the dimension you're stuck moving through and the dimensions you can navigate freely, temporarily disappears. I'm sitting with a cup of tea that went cold about 20 minutes ago, and I keep picking it up and putting it back down without drinking it, which is genuinely the right physical context for thinking about imaginary time, because imaginary time is one of those concepts that feels like it should be colder than it is, more alien, and it is alien in some ways. But it's also, once you've spent time with it, oddly natural. The rotation is clean, the mathematics behaves well. What Hawking and Hartley proposed is that in imaginary time, the universe has no beginning. In imaginary time, the geometry of space-time near the Big Bang is not a cone, sharp point at the bottom, opening outward, but a sphere, smooth all the way around, no edge, no boundary. The way the surface of the Earth has no edge, no point where it simply stops and you fall off into nothing. Here's the analogy Hawking returned to repeatedly, because it is genuinely the right analogy, even though it's simple enough to feel almost too simple. Think about the surface of the Earth. Stand at the South Pole. Now walk north, in any direction, since all directions from the South Pole are north. As you walk north, you're moving away from the pole in what feels, locally, like a straight line. The pole is behind you. There's a before the pole in the sense that you were there and now you aren't. But ask yourself, what is south of the South Pole? Nothing, not an empty space, not a void, not a wall. The question fails to refer to anything. South is a direction defined by the geometry of the sphere, and at the South Pole that direction has no continuation. You can't go further south because south at that point simply ceases to be a direction. Hawking's proposal is that time near the Big Bang in imaginary time behaves the same way. Before is a direction, and like south at the South Pole it runs out, not into a wall, not into a void, but into a geometry that no longer supports that direction. Asking what happened before the Big Bang, Hawking said, is like asking what lies south of the South Pole. It is not that there is nothing south of the South Pole, it is that the concept of south loses its meaning there. This, and I want to be careful here because I think this deserves to be said carefully, is not a dodge. It sounds like one. It sounds like Hawking is saying the question is meaningless, in order to avoid answering it, the way a politician pivots from a question they don't want to answer. But it isn't that. The meaninglessness in this proposal is structural. It emerges from the geometry itself. The proposal doesn't say we don't know what was before. It says the geometry of space-time near the beginning is such that before, as a direction, as a relation between moments, doesn't extend there. The question doesn't lack an answer. It lacks a referent. Now, the proposal does something else too, which often gets less attention than the South Pole analogy. If the universe in imaginary time is a smooth closed geometry, a sphere roughly with no boundary, then there are no special initial conditions to specify. The sphere doesn't have a bottom. It doesn't have a starting point from which everything else must be measured. It's complete in itself. The wave function of the universe, Hartley and Hawking's term for the quantum description of the whole universe, the probability amplitude for all possible geometries and matter configurations, is determined by summing over all compact geometries with no boundary. No external input required. The universe in this sense is self-contained. It doesn't need a cause outside itself, because it doesn't have a boundary at which a cause could be applied. Whether this is satisfying or deeply unsatisfying probably depends on what you are hoping to find. Some people hear the universe is self-contained and feel a kind of relief, a closed loop, something complete. Others hear it and feel a different kind of vertigo. If there's no cause, no boundary, no initial moment from which the clock started, then what does it even mean to say the universe exists rather than nothing? That question, the question of why there is something rather than nothing, which is technically a philosophical question and not a physics question, though the line is blurry here, is one the no-boundary proposal doesn't really address. It dissolves the question of what came before the Big Bang, but it doesn't answer why there is a universe at all. That's a different question, maybe a harder one. The proposal has critics, serious ones, including other serious physicists who find the mathematics of the path integral used in the no-boundary formulation difficult to pin down precisely, who argue that the Euclidean approach, the imaginary time geometry, doesn't straightforwardly translate back to real physics, who question whether the most probable universe that emerges from the proposal looks like the one we actually live in. Neil Turok, who has collaborated with Hawking on other things and clearly respects the work, has nonetheless argued that the no-boundary proposal, when computed rigorously, may predict a universe different from the one we observe. These are real objections. The no-boundary proposal is not finished physics. It is a framework, a direction, a deeply elegant idea that hasn't yet been fully vindicated by calculation or observation. And yet, there's something about its central move, the dissolving of before into a smooth geometry rather than a wall, that feels, to me anyway, like it's pointing at something true, even if the specific mathematics isn't yet complete. The instinct that the question what was before the beginning contains a hidden flaw, that it imports a structure time doesn't actually have at that scale. That instinct, whatever its precise mathematical form turns out to be, seems right. The South Pole doesn't go anywhere when you stand on it. It just stops being south. Time, at the beginning, or at what we call the beginning, may do something similar. Not stop exactly, not end in a wall, just quietly cease to be the direction we thought it was, and somewhere in the space between that ceasing and the universe we actually inhabit, something happened that we're still learning how to describe. There is a room, no windows, no doors, not locked, just absent. No clock on the wall, because there is no wall exactly, just the sense of enclosure without boundary. You are not in the room. There is no you in this image. There is just the room, and the room has extent. It occupies something, it has dimensions, but nothing in the room is changing. Nothing is moving toward anything else. Nothing is earlier or later than anything else. This is not emptiness. Emptiness is a spatial concept, a place where things could be but aren't. This is something harder to name, a geometry without sequence. In the Hartley-Hawking framework, what exists near the beginning, in imaginary time, in that region where the shuttlecock rounds off rather than sharpening to a point, is not a void waiting to be filled. It is a four-dimensional geometry in which all four dimensions behave spatially, not three spatial dimensions plus one time dimension. Four spatial dimensions, a smooth, closed, finite geometry, a kind of hypersphere. On a hypersphere, there is no preferred direction, no axis that functions differently from the others, no dimension along which you are required to move, only forward, only increasing. Every direction is equivalent. Every path through the geometry is as valid as every other path. In ordinary space-time, the space-time you and I inhabit right now, the space-time that has been expanding since the early universe, time is not like that. You move through it in one direction. You don't choose to. The distinction between past and future is not a convention. It is physical, enforced by thermodynamics, by the increase of entropy, by the simple fact that broken things don't spontaneously reassemble. Time has an arrow and the arrow is not optional. But in the region Hartle and Hawking describe, that arrow doesn't exist yet. Can't exist yet. Because the dimension that will become time hasn't yet become time. It is still in the imaginary time description, just another spatial direction, equivalent to the others, undifferentiated. I find this, and I'm aware this might be a strange thing to say, more disorienting than the singularity. The singularity is at least a crisis, a breakdown, something dramatic you can point to. This is quieter than that. This is the suggestion that there was a phase of the universe's existence, if phase and existence and was even apply, in which the ingredient that makes sequence possible simply wasn't operating as sequence. Space without the arrow. Geometry without before and after. Not darkness. Darkness is a visual concept, and vision requires time, a photon travelling from a surface to a detector, a duration, a sequence of events, not silence either. Silence is what you have when sound has stopped, and stopping is a temporal idea, just geometry. Sitting there, and even sitting there is wrong, because sitting implies duration, implies a moment when the sitting began, and a moment when it will end. The language keeps failing. That's not a weakness of the explanation, it's the actual content. What Hartle, in an interview years after the original paper, said about "this is worth holding on to," he said, "We didn't have birds in the very early universe. We have birds later. We didn't have time in the early universe. We have time later. The emergence of time, the transition from the imaginary time geometry to the real-time geometry we inhabit, is, in the no-boundary picture, something like the emergence of a direction from a geometry that didn't have preferred directions. It's a transition. A phase change almost, though that analogy has limits. And like most phase changes, it doesn't require an external cause. Water doesn't need something to tell it to freeze. Below a certain temperature, given the right conditions, the transition happens because the physics allows it and the conditions are met. Ice has a structure that liquid water doesn't. The structure emerges. Time may have emerged similarly, not from nothing, from a prior geometry that didn't yet distinguish temporal from spatial. The arrow appeared because the conditions for an arrow were met. The universe, having existed, in whatever sense, as pure spatial geometry, transitioned into something that had a direction, a sequence, a before and after. And once that happened, once time was time, the expansion we described in the previous chapter began. The corridor opened, 14 billion years of it, give or take. The specific moment of that transition is not something the no-boundary proposal describes with precision. It describes the geometry of the region where time is not yet time. It describes the large-scale shape of the universe once time is operating normally. The transition between them, the precise mechanism of time's emergence, is still honestly not fully worked out. This is where I want to resist the pull toward false tardiness. It would be easy to present the no-boundary proposal as a complete picture, a solved problem. It isn't. It is a framework with genuine mathematical content, with real predictive power in some regimes, and with gaps and unresolved difficulties in others. The emergence of time, how exactly the imaginary time geometry becomes a real-time cosmology, is one of those gaps. But the conceptual move it makes is real regardless of whether every mathematical detail is settled. The move is this: before time was time, there was something, not nothing, not a void, not an absence, a geometry, spatial, closed, finite, without sequence or directional arrow, space before time, not space waiting for time to begin, not an empty stage, just space. Doing whatever space does when there is no time for it to do it in, which is, as far as anyone can tell, simply existing, quietly, without event, without before or after, until somehow it wasn't like that anymore. Compress something far enough and it pushes back. You know this, not as physics, as experience. Press your palm flat against a table. Feel the table press back. Squeeze a rubber ball until your knuckles whiten. The ball resists. Pack enough people into a small enough space, and the crowd itself becomes a pressure, a physical thing you can feel against your ribs even before anyone moves. Compression generates resistance. This is so ordinary, so woven into every physical interaction you've ever had, that it barely registers as a fact worth noting. But at the Planck scale, at densities so extreme they make neutron stars look like clouds, something similar happens, and the consequences are not ordinary at all. Loop quantum gravity begins from a specific premise, that space is not continuous, not smooth fabric, infinitely divisible, capable of being curved into arbitrarily tight configurations. Space in this framework is granular. It has a smallest unit, the Planck length, roughly 10 to the negative 35 meters, below which the concept of distance stops meaning anything. Not because our instruments are too crude to measure it, because there is nothing to measure. Smaller than the Planck length is not a place. This is a significant departure from general relativity, which assumes smoothness all the way down. General relativity can describe a singularity because smooth space-time under sufficient curvature can keep curving without limit. Nothing in the classical equation says stop. But if space is granular, if there is a minimum length, a minimum volume, an atomic structure to geometry itself, then the curvature cannot increase without limit. At some point, the geometry is fully packed, saturated. There is no more room to curve, and when there is no more room to curve, gravity, which in loop quantum cosmology behaves repulsively at these extreme densities, pushes back. Abhay Ashtekar at Penn State, working with colleagues through the early 2000s, formalized this into what became loop quantum cosmology. The specific result that matters here is this. In the models they analyze, the Big Bang singularity does not occur. The backward extrapolation that classical general relativity insists must end in infinite density and infinite curvature, the place where the equations blow up, instead hits the Planck density, finds a repulsive quantum pressure waiting there and bounces. Not explodes, not ruptures, bounces. The universe in this picture did not begin, it contracted. Something, some prior cosmological epoch, some prior expanding phase, contracted under gravity, grew denser, approached the Planck scale, and instead of collapsing into a singularity, encountered the quantum geometry of space itself as a kind of flaw, a hard limit, the contraction reversed. What we call the Big Bang is, in loop quantum cosmology, the moment of that reversal, the bounce point, the minimum volume, the instant when contraction became expansion, which means there was a before, a genuine, physical before, not a before in imaginary time, not a before that dissolves under scrutiny. An actual prior epoch, a universe that existed before the one we live in, connected to ours through a quantum bridge at the Planck scale. Now, and this is where I want to slow down slightly, this is not the same as saying loop quantum cosmology is correct. It isn't established the way that, say, the expansion of the universe is established. It is a framework, a technically sophisticated, mathematically serious framework with peer-reviewed results and ongoing active research, but a framework nonetheless. The specific models Ashtekar and colleagues analysed are simplified. They use symmetry-reduced cosmological spacetimes, which means a lot of the messy inhomogeneity of the real universe gets smoothed away for tractability. Whether the bounce result holds in fully inhomogeneous settings, whether it survives the inclusion of all the degrees of freedom a real universe would have, is still being worked out. I keep coming back to this because it matters. Not to undersell the physics is genuinely interesting, but because one of the things I find most honest about this field is how carefully the people doing it tend to distinguish between what the models show and what the universe actually does. That caution is not weakness. It's the thing that makes the work trustworthy. So, the models show a bounce. The question of whether the real universe bounced is still open. But set the qualification aside for a moment. Just hold the picture. A universe contracting. Not slowly, not gently, at cosmological rates, which are enormous by human standards, but gradual on the scale of deep time. The matter and energy of that prior universe compressing into smaller and smaller volumes, the temperature rising, the structures, whatever structures existed in that prior epoch, whatever galaxies or their equivalent, whatever large-scale geometry had formed over however many billions of years, dissolving back into undifferentiated plasma as the compression heated everything past the point where complex structure could survive. And then, at the very bottom of the contraction, at the Planck density where quantum geometry makes gravity repulsive, the compression reverses. The stuff, and it is stuff at this point, undifferentiated, ferociously hot, structureless, begins expanding. The temperature falls, particles form, nuclei form, atoms form. The universe we know begins its 13.8 billion years of expansion. From the outside, if there were an outside, if there were someone watching, where it would look less like a beginning and more like a breath. An inhale, long and deep, followed by a moment of held stillness at the Planck scale, followed by an exhale that is still going. We are in the exhale. There's a detail here that I find quietly remarkable, maybe more than the bounce itself. In loop quantum cosmology, the equations are deterministic across the bounce. The quantum evolution of the universe's wave function doesn't stop at the minimum volume and restart on the other side. It continues, smoothly, through the bounce point, from the contracting branch to the expanding branch in a single unbroken mathematical thread. This means, in principle, not yet in practice, that information about the prior epoch is not destroyed. It crosses the bounce. It is encoded, in some form, in the state of the universe immediately after. The conditions of our Big Bang, the specific energy density, the specific fluctuations that seeded all the structure we observe, are not arbitrary initial conditions in this picture. They are consequences of what came before. They are the bounce's memory. Whether we could ever actually read that memory, whether any observable feature of the current universe could be traced back to a specific feature of the prior contracting phase, that is an active research question. There are proposals. Some involve specific signatures in the cosmic microwave background, specific patterns in the power spectrum of primordial fluctuations that loop quantum cosmology predicts would differ subtly from standard inflationary predictions. The differences are small. Whether future experiments can resolve them is not yet clear. What loop quantum cosmology does, most fundamentally, is remove the singularity not by philosophically dissolving the question, the way the no-boundary proposal does, but by replacing the singularity with a physical event. A bounce. A moment of minimum volume. A thing that happened. This feels different. It feels, and I want to be precise about this being a feeling, not a conclusion, more like a before in the ordinary sense, a previous state of physical reality, not a prior geometry that transitions into time, not a condition where the question of before loses grammatical footing. Just, the universe was smaller, then smallest, then larger. A sequence, a real one. Whether that prior universe was itself preceded by another bounce, and that one by another, whether the cosmos is cyclic in the deep sense, an infinite series of expansions and contractions, is a separate question, and one that runs into the second law of thermodynamics in ways we'll look at shortly. The single bounce picture doesn't require an infinite chain. It just requires one prior contraction, one exhale before this inhale. That is, on the scale of what this chapter has been exploring, a remarkably modest claim. And somehow that modesty makes it feel more plausible, not less. Not a grand cyclic cosmos of infinite age, just something contracted, something bounced, something expanded, and what expanded became everything we've ever known. Everything moves toward disorder, not quickly, not dramatically. The universe is patient about this in a way that makes human impatience look almost charming, but consistently, without exception, without negotiation. A hot cup of something left alone grows cold. A drop of ink in water spreads. A tidy room, uninhabited long enough, accumulates dust, then clutter, then a different kind of quiet. None of these processes run backward on their own. The cold cup doesn't reheat. The ink doesn't reconcentrate. The room doesn't tidy itself. This is entropy, the measure of disorder in a system. And the second law of thermodynamics, one of the few laws in physics that has a direction, that cares about before and after, says it always increases. In any closed system, over time, entropy increases or stays the same. It never spontaneously decreases. The second law is not like other laws. It doesn't describe a force. It doesn't give you an equation of motion. It gives you a direction, an arrow, and that arrow, quiet and patient and utterly indifferent to whatever cosmological framework you prefer, has something important to say about universes that bounce. Cyclic cosmologies are beautiful, worth saying that plainly before anything else. The idea that the universe contracts and expands in an endless rhythm, that our Big Bang was one beat in an infinite series of beats, that the cosmos has always existed and always will, has a quality that feels almost restful. No true beginning, no true end, just the breath over and over. Paul Steinhardt at Princeton explored this seriously. Neil Turok collaborated on versions of it. These are not fringe proposals worked out on napkins. They're technically developed, mathematically serious attempts to build a cosmology without a singular beginning. And they have genuine virtues. They sidestep the initial conditions problem. They offer a mechanism for why our universe looks the way it does. They are, in certain respects, elegant. And then the second law walks in. Here is the problem, stated simply. Each cycle of a cyclic universe, each expansion phase, each contraction phase, is a physical process. Physical processes generate entropy. The entropy of the universe at the end of one cycle is higher than at the beginning of that cycle. It must be. The second law doesn't have exceptions, not even for cosmological scales, not even for universes, which means the next cycle begins with more entropy than the last one ended with, and the one after that begins with more still. Each cycle is more disordered than the previous. Each contraction begins from a higher entropy state. Extrapolate this forward, and cycles become longer, more diffuse, more featureless as entropy accumulates. Extrapolate it backward, and cycles become shorter, more ordered, lower in entropy. Keep going backward and you run out of cycles. The entropy can't keep decreasing indefinitely. There is a minimum entropy, a maximum order, a starting point below which you cannot go. The infinite regress of cycles hits a wall, not a physical wall, a thermodynamic one. Roger Penrose made a version of this argument with particular sharpness, a universe cycling through contraction and expansion. If it's carrying its entropy forward from one cycle to the next, cannot be infinite into the past. Somewhere back there, the entropy was lower, and lower, and lower still. Until you're asking about a beginning again, just a beginning dressed differently. Steinhardt and Turok, aware of this, developed versions of their ekpyrotic and cyclic models that attempt to address the entropy problem. Models in which the entropy is, in some sense, diluted or reset across the transition between cycles. The mechanisms are technically complex, and the debate about whether they actually solve the problem or merely reframe it is ongoing. Some physicists find the proposed solutions compelling. Others find them incomplete. This is, I want to be honest about this, not a settled question. The entropy problem with cyclic cosmologies is a genuine problem. It doesn't definitively kill the idea. It constrains it. It demands that any serious cyclic model explain how the entropy accounting works across the bounce or the transition. Some models have answers. Whether those answers are correct is still being argued. But there's a harder version of the problem, one that sits underneath the entropy debate and doesn't move when you push it. The Border-Guth-Vilenkin theorem, published in 2003, Arvind Border, Alan Guth, Alan Vilenkin. What they proved, and it is a proof, not a conjecture, is that any spacetime that is, on average, expanding must be geodesically incomplete to the past, which means any universe that has been expanding on average, no matter how long, no matter what cosmological model describes it, must have had a beginning. A point in the past before which the mathematical description breaks down. The theorem is more general than it sounds. It doesn't assume general relativity holds in any particular form. It doesn't assume specific energy conditions. It applies to inflationary universes, bouncing universes, cyclic universes, any spacetime that is expanding on average. And our universe has been expanding on average, observationally, definitively. What the theorem says then is that eternal inflation, the picture of a universe that has always been inflating, always been producing bubble universes like ours, stretching infinitely into the past, is not viable. The inflationary spacetime cannot be extended indefinitely backward. It was geodesically incomplete. It had a beginning, or something that functions mathematically like one. Vilenkin, who is not prone to overstatement, put it this way. Although inflation may be eternal into the future, it cannot be extended indefinitely to the past. This is the door the second law keeps holding closed, in various forms, across various frameworks. You can sidestep the singularity. You can dissolve the question of before into a smooth geometry. You can propose a bounce, a mirror universe, a tunneling from nothing. But the arrow of time, that patient, unglamorous, deeply fundamental asymmetry, keeps appearing in the corner of every framework and asking the same question. How did the entropy get so low? Because the early universe was extraordinarily low entropy. The cosmic microwave background, that smooth, nearly uniform afterglow, smooth to 1 part in 100,000, represents a state of extraordinary order by any thermodynamic measure. A hot, dense, nearly uniform plasma is not a disordered state. It is a highly ordered one. The universe began somehow, in a state of remarkable low entropy and has been increasing in entropy ever since. Any cosmological model, any model at all, has to account for that, has to explain how you start a universe in a low entropy state. The Singularity didn't answer this. The bounce has to answer it. Where did the pre-bounce universe get its low entropy from? Eternal inflation has to answer it. If inflation is past eternal, why was the entropy ever low? The no-boundary proposal has to answer it. The smooth, closed initial geometry it describes is, arguably, precisely the kind of low-entropy initial condition needed. But why that geometry rather than a higher entropy one? There is something sitting in the corner of every room in this building. It doesn't raise its voice. It doesn't announce itself. It just keeps being there, and the longer you sit with it, the more central it becomes. Entropy began low. Everything since has been the universe spending that extraordinary initial order, slowly over 13.8 billion years and counting, into the gradual, patient, inevitable drift toward equilibrium. All the structure you've ever seen, every galaxy, every star, every warm thing in the cold dark, is that spending, that dissipation. And what it was spent from remains, in the deepest sense, unexplained. Alan Guth was not trying to find a beginning. In 1981, when he proposed inflation to that brief, violent, exponential expansion in the universe's first fraction of a second, the goal was to solve a different set of problems entirely. Why is the universe so flat? Why does the cosmic microwave background look almost identical in every direction, even in regions that, by standard Big Bang physics, could never have been in contact with each other? Why are there no magnetic monopoles, those exotic relics that grand unified theories predicted should be everywhere but aren't? Inflation answered all of these. Space expanded so rapidly, so early, that whatever irregularities existed were smoothed out. Whatever monopoles formed were diluted to near zero density. And regions that now appear causally disconnected were, before inflation, close enough to reach thermal equilibrium. It was a genuinely beautiful solution, not immediately accepted, that took years. And the CMB data that eventually confirmed inflation's specific predictions, but beautiful in the way that solutions are beautiful when they dissolve four problems simultaneously by introducing one mechanism. And then people noticed something about what inflation implied for the past. If inflation works, if the universe underwent exponential expansion very early, then the equations describing that inflationary phase have a specific property. In most inflationary models, the expansion never completely stops everywhere at once. In the regions where it stops, you get a hot, dense universe like ours, matter and radiation filling the space where inflation ended. But in the surrounding regions, inflation continues. And in those inflating regions, space is expanding so rapidly that new volume is being created faster than inflation can end within it. The inflating space outpaces the pockets of non-inflating space. This is eternal inflation. The picture in which our universe is one bubble, one region where inflation stopped, floating in a vast, possibly infinite sea of still inflating space, which is itself producing more bubbles constantly, which has presumably always been doing this. Alexander Vilenkin at Tufts was one of the people who worked out the details of this, who showed that eternal inflation is not a special case or an edge condition, but a generic feature of inflationary models. In the eternal inflation picture, there is no beginning. Inflation always was. Bubble universes like ours are produced endlessly. There is no first moment. The multiverse stretches infinitely into the past. It is a picture that many physicists found and still find philosophically attractive. No beginning required, no initial conditions to explain, just an eternal, self-reproducing process. Vilenkin, Guth, and Arvind Border sat down with this picture in 2003 and asked it a very specific question. Not, is it beautiful? Not, is it consistent? Just, can an inflating space-time actually be extended infinitely into the past? Given the mathematics of expansion, given the geometry of space-time in an inflating universe, is past eternal inflation actually mathematically viable? What they found and proved is that it isn't. The argument goes roughly like this. In an expanding space-time, consider any observer, any particle, any galaxy, anything moving through that space. Now trace that observer's path backward in time. Because the space around the observer is expanding, the observer's velocity relative to any reference frame they pass through, relative to the local expansion, is being stretched. Going backward, that velocity increases. Keep going back far enough and the velocity approaches the speed of light relative to the background expansion. At that point, the mathematical description of the observer's path breaks down. The geodesic, the path through space-time, is incomplete. It simply ends. Not at a singularity necessarily, not at infinite density, just at a point beyond which the mathematics cannot be extended. An incomplete geodesic means the space-time itself is incomplete. Mathematically, physically, a space-time that can't be extended backward is one that had a beginning, or, more precisely, one that cannot be described as having existed infinitely into the past. The theorem states, any space-time region that had been expanding on average, not uniformly, not everywhere, just on average, and must be geodesically incomplete to the past, must have a boundary, must have something that functions mathematically as a beginning. The on-average clause is important. This is what makes the theorem so broad. It doesn't require continuous expansion. It doesn't require inflation everywhere. It just requires that the expansion averaged across the space-time region in question is positive. Our universe satisfies this. Eternal inflation satisfies this. Most bouncing cosmologies satisfy this. The theorem casts a very wide net. Vilenkin was clear-eyed about what this meant. In the years after the paper, asked repeatedly whether the theorem proves the universe had a beginning, he gave answers that were careful, honest in the specific way that careful physicists are honest when they've proved something they know people will misuse. The theorem shows that inflationary spacetime cannot be eternal to the past. Yes, it has a past boundary. But the theorem says nothing about what that boundary is, nothing about what came before it, if before applies, nothing about whether the boundary represents a true beginning or a transition from some prior non-inflationary phase. He said, in one interview, something that has stuck. I cannot really claim that I understand the beginning of the universe. We have a picture which kind of makes sense, which I think is an achievement. That sentence deserves to just sit there for a moment, which kind of makes sense. From one of the people who proved that even eternal inflation had to start somewhere, a picture which kind of makes sense, not certainty, not triumphant resolution, just a picture. That kind of makes sense. From a physicist who spent decades working on the very questions that the theorem raised. There's something in that honesty that I find more grounding than any clean answer would be. Not because uncertainty is comfortable, it isn't, but because it's accurate. The BGV theorem is real mathematics. Its conclusion is solid within its assumptions. What it cannot do, what no theorem can do, is tell you what the boundary actually is. Whether it's a genuine beginning of time, whether it's a transition from a prior phase, whether it's the place where one description of the universe hands off to a different description that we haven't yet fully built. The theorem closes a door, the door that said inflation could sidestep the beginning entirely, that the universe might have been inflating forever, that past eternal expansion could just keep going. That door is closed. But it opens into a hallway, not a room. The question of what the boundary represents, what lies at or before it, whether before is even the right preposition, remains exactly as open as it was before the theorem existed. Vilenkin, Border and Guth found the edge of the map again, a different edge than the one general relativity found, arrived at by different means, but still an edge, and just past it, the same question is waiting, unchanged, patient as entropy. There is a specific moment standing at a window at night when the glass stops being transparent and becomes a mirror. The light outside drops below a threshold, and suddenly what you see is not the street or the sky, but yourself, your own face, the room behind you, everything familiar, but laterally inverted. Left become right, right become left. The reflection has always been there. The glass was always capable of it, but you only see it when the conditions are right, when the outside goes dark enough that the inside light dominates. Latham Boyle, Kieran Finn and Neil Turok published a paper in 2018 that most science journalists did not quite know what to do with. It appeared in Physical Review Letters, which is not an obscure venue. The mathematics was serious. The proposal was, in a certain light, almost conservative. It didn't introduce new fields, didn't require new particles beyond what the standard model already contains, didn't invoke strings or extra dimensions or exotic mechanisms. What it proposed was something more unsettling than any of those things, because it was so clean. The universe, they suggested, does not violate CPT symmetry. CPT symmetry is one of the deepest symmetries in physics. C stands for charge conjugation, the operation of flipping every particle to its antiparticle, every positive charge to negative, every electron to positron. P stands for parity, flipping spatial coordinates, turning left into right, mirroring every physical process through a point. T stands for time reversal, running every process backward, every cause becoming effect, every arrow of time inverted. Individually, some of these symmetries are broken by the universe. The weak nuclear force, for instance, distinguishes between left and right. It violates parity, which shocked physicists in 1956 when Chien-Shiung Wu's experiment confirmed it. The universe also appears to violate the combination of C and P simultaneously, called CP violation, in certain particle decays. And time reversal at the macroscopic level is obviously broken. You can tell a film is running backward because broken things don't spontaneously reassemble, because entropy increases in one direction. But CPT together, all three operations simultaneously, is thought to be an exact symmetry of any consistent quantum field theory. It's not an experimental finding exactly. It's more like a theorem embedded in the structure of quantum field theory itself. Flip charge, flip parity, flip time, all at once, and the physics should be identical. What Boyle, Finn and Turok noticed is that our universe, as observed, seems to violate this, not in the equations, but in the boundary conditions. Our universe has more matter than antimatter. Time runs in one direction, space has a specific orientation. The universe looks, in CPT terms, lopsided, and a universe that is lopsided in this way is one that implicitly has a mirror image it isn't paired with. Their proposal, it is paired with one. We just can't see it. The picture goes like this. The Big Bang is not a beginning in their framework. It is a boundary, a point of symmetry, a mirror surface, at which two universes meet. On our side of the bang, time runs forward, matter dominates, left is left. On the other side, time runs backward, relative to our time, which means forward relative to the inhabitants of that universe, if there were any. Antimatter dominates, and left and right are swapped. The two universes are CPT images of each other. Together, the pair is CPT symmetric. The universe as a whole obeys the symmetry we. Each half, looked at alone, appears to violate it. This is, and I want to sit with this for a moment before moving on, a genuinely strange idea. Not strange in the way that extra dimensions are strange, where the strangeness is the point and you're being asked to accept something with no intuitive foothold. Strange in the way that the window reflection is strange when you first really notice it. The reflection was always there, governed by straightforward physics, and yet the moment you actually look at it as a thing in itself, rather than a distraction, it feels briefly wrong, like the room doubled in a way it shouldn't have. The antimatter universe running backward in time was always implied by CPT symmetry. Boyle, Finn and Turok just took that implication seriously as a physical reality rather than a mathematical curiosity. What comes out of taking it seriously is more than just philosophical tidiness. The model makes predictions, real ones, the kind that can in principle be confirmed or ruled out by observation. One involves gravitational waves from the early universe, the primordial gravitational wave background that inflationary models predict should exist, imprinted on the cosmic microwave background as a specific pattern called B-mode polarization. In the CPT symmetric model, this background has a specific character that differs from standard inflationary predictions. If it's detected, and if it matches the standard inflationary pattern, the CPT symmetric model is in trouble. If it isn't detected, or if the pattern is different, the model survives and gains ground. Another prediction involves dark matter. In the CPT symmetric universe, dark matter finds a natural candidate that requires no new physics beyond the standard model, a specific type of neutrino called a sterile neutrino, one of the right-handed neutrinos that the standard model already has room for but doesn't require. The mass of this dark matter candidate, calculated from the model's requirements, comes out to approximately 4.8 times 10 to the 8th giga-electron volts, a specific number, a testable prediction, not an adjustable parameter. This is what distinguishes a serious proposal from speculation. It says, here is what we would see, and here is what we would not see, and the difference matters. The entropy problem, the one that cornered cyclic cosmologies in the last chapter, appears here too, and it behaves differently. In the CPT symmetric model, both universes emerge simultaneously from the bang with low entropy. The low entropy is not inherited from a prior state. It's a consequence of the symmetry itself. The bang is a point of maximum symmetry, which corresponds to minimum entropy, and both universes evolve away from it in opposite temporal directions. The second law operates in both universes, entropy increasing in each as both move away from the symmetric boundary. The low entropy at the beginning is not an assumption. It's a prediction of the geometry. Whether this fully resolves the entropy problem depends on how you account for entropy in a two-sheeted spacetime, which is a subtle question that Boyle and colleagues have addressed in follow-up papers, but which remains an area of active work. It's not settled, but the mechanism is at least coherent, which is more than can be said for some of the alternatives. There is something I find difficult to let go of when I think about this proposal, and it isn't the mathematics. It's the image. The idea that on the other side of the moment we call the beginning, not before it in time because time runs the other way over there, but on the other side of it as a boundary, there is something. Not nothing, not a void, not a condition where the question of existence loses meaning. A universe, running in a reverse made of antimatter, mirror left to our right. It has never interacted with ours, cannot interact with ours. The bang boundary separates them completely, and even if it didn't, matter and antimatter annihilate on contact. They are permanently, structurally isolated. We will never see evidence of it directly. Its galaxies, if it has galaxies, its stars, its 13.8 billion years of expanding structure, all of it completely invisible to us on the other side of a boundary we call the beginning. But it might be there. The physics allows it, more than allows, requires it, if CPT symmetry is exact and the universe is not spontaneously breaking it. The window works both ways. We are the reflection in someone else's glass. Or perhaps, and this is the thought I can't quite dismiss, there is no someone else. The antimatter universe doesn't have observers in the way ours does, or has them in a form so different that the comparison breaks down. It exists as a mathematical necessity, a CPT image, a shadow that the symmetry of physics casts whether or not anything in it is watching. The bang is not an explosion in this picture. It is a mirror, and we are one side of it. Nothing is a word that gets used too loosely. When physicists say the universe might have emerged from nothing, they don't always mean the same thing. Some mean a quantum vacuum, a seething, fluctuating field state that is the lowest energy configuration of space, but is still a space, still has geometry, still has quantum fields threading through it doing their probabilistic work. That is not nothing, that is something very specific with mathematical structure and physical properties and a well-defined relationship to the particles that pop in and out of it. The quantum vacuum is not empty in any ordinary sense of the word. Some mean a prior state, a contracting universe, an inflating region, a pre-bang geometry. Also not nothing, something that existed, something physical, something that obeyed laws. What Alexander Vilenkin means, when he uses the word, is different. He means the literal absence of space-time, not empty space, not space with nothing in it, the absence of space itself. No geometry, no dimensions, no quantum fields, because quantum fields require a space-time to live in. No time, because time is a dimension of space-time. The absence specifically of the substrate that everything else requires in order to exist, that is a different kind of nothing. And it is from that, from the literal absence of everything, including the container that everything else needs, that Vilenkin proposes the universe tunneled into existence. Quantum tunneling is a real phenomenon, not a metaphor, not an analogy borrowed from particle physics to make cosmology sound more dramatic. It is one of the most well-confirmed predictions of quantum mechanics, observed daily in transistors, in nuclear fusion in the sun, in the alpha decay of radioactive nuclei, the basic mechanism. A particle encounters a barrier that classical physics says it cannot cross. Its energy is insufficient. The potential hill is too high. Quantum mechanically, the particle's wave function doesn't stop at the barrier. It extends through it with exponentially decreasing amplitude. There is a non-zero probability that the particle will be found on the other side. It tunnels. The rate depends on the barrier's height and width. For a thin, low barrier, tunneling is fast and frequent. For a thick, high barrier, it's slow and rare. But as long as the barrier is finite, as long as the probability is not exactly zero, tunneling happens. Eventually. What Vilenkin proposed, beginning in the early 1980s and developing through subsequent decades, is that the universe itself underwent a tunneling event, not a particle tunneling through a potential barrier. The entire universe, all of space-time, all of its initial energy and geometry, tunneling from a state of nothing into existence. The formal structure of this involves the wave function of the universe. Not a particle's wave function, but a wave function defined over all possible three-dimensional geometries, all possible spatial configurations the universe could have. Hartle and Hawking had their version of this wave function, derived using the no-boundary path integral. Vilenkin had his, derived using a different boundary condition. Instead of no boundary, he specified a boundary at nothing, at zero geometry, and asked what the wave function looked like propagating away from that boundary. What came out was a probability distribution over possible universes. Small universes, large universes, universes with different geometries and different energy densities, not all equally likely. The probability of a universe with a given geometry and a given inflationary energy scale could, in principle, be calculated. The most probable universe, the one with the highest tunneling probability, turned out to be a small universe with a large inflationary energy, which then underwent rapid expansion. Inflation, in other words, is not something Vilenkin had to add to the picture separately. It emerged from the tunneling itself. The universe tunneled into existence already set up to inflate. Here is where I find myself wanting to be careful, because the picture is genuinely striking, the universe appearing from nothing, fully formed enough to immediately begin inflating. And striking pictures have a way of overreaching their evidence without anyone noticing. What Vilenkin showed is that if you set up the wave function of the universe with a specific boundary condition at nothing, if you apply the mathematics of quantum tunneling to that wave function, if you accept the technical framework of quantum cosmology, then you get a non-zero probability for a universe to appear. The mathematics is consistent. The result is not arbitrary. It makes predictions about the inflationary spectrum that have, in broad terms, been consistent with CMB observations. But the boundary condition, the decision to define the wave function at nothing rather than at some other state, is itself a choice. A motivated choice, a mathematically natural one, but a choice. And the framework of quantum cosmology, which applies quantum mechanics to the universe as a whole, is not an established theory in the way that quantum electrodynamics is established. It is a research program, a serious one, with real mathematical content and real predictive power in certain regimes, but not finished, not tested in the way that makes physicists comfortable saying, this is how things are. So, the universe may have tunneled from nothing. The mathematics allows it. The probability, while small, is non-zero by construction of the framework. Whether the framework is the right one, whether quantum cosmology in this form is actually describing reality, is the part that remains genuinely open. There is a specific philosophical knot here that Vilenkin does not pretend to untie. The tunneling process, even in ordinary quantum mechanics, is a process. It takes, in some sense, a configuration of possibilities, a wave function, a set of quantum mechanical rules. In the case of a particle tunneling through a barrier, the wave function exists in space and time. The barrier exists in space and time. The rules of quantum mechanics operate in space and time. Even the nothing from which the universe tunnels in Vilenkin's picture is not quite featureless. It is a state described by the wave function of the universe set to zero geometry, which still requires a mathematical framework to describe, which still requires, at some level, the laws of quantum mechanics to be operative. Where do the laws come from? Vilenkin has addressed this directly, honestly. He has said that the laws of physics, quantum mechanics, the rules that govern the tunneling, may exist independently of the universe. Not in a space, not at a time, but as abstract mathematical structures that are simply true, the way the Pythagorean theorem is simply true regardless of whether anyone is around to prove it. The universe tunneled because the laws allowed it. The laws don't need a location or a medium, they just are. This is not a comfortable answer. It's barely an answer at all, in the sense that it trades one mystery for another. But it is an honest one. The most honest version of the proposal does not claim to have reached bedrock. It claims to have reached a layer of foundation below which the tools of physics, at least the tools we currently have, cannot reach. What I keep returning to, late in the night, in the specific silence of a house that has gone completely still, is this. The universe tunneling from nothing is not more mysterious than the universe simply existing. It might be less so. A universe that appeared, that had a mechanism, however strange, however incomplete, is at least a universe that happened for a reason we can write down, can calculate with, can test in its predictions. The alternative, a universe that simply is eternally, without any account of why, is also mysterious, just quietly so quietly that we rarely notice we haven't explained it. Vilenkin's nothing is loud by comparison. It insists on being thought about, and somewhere in that insistence, in the refusal to accept it just exists as a final answer, there is something that feels, if not like progress, then at least like the right kind of restlessness, the kind that keeps the question alive. Not all limits are temporary, some of them are. The limit of not knowing the composition of the cosmic microwave background in enough detail, that was temporary, dissolved by better instruments, better detectors, decades of increasingly precise measurement. The limit of not knowing whether the expansion of the universe was accelerating or decelerating, temporary, ended in 1998 when two independent teams studying distant supernovae discovered, to their own surprise, that it was accelerating. Many of the limits in cosmology are of this kind. Limits of technology, of sensitivity, of time. They yield. They have been yielding steadily across a century of modern astronomy. But there is another kind of limit. Not a limit of what we can currently measure, but a limit of what there is to measure. Not a gap in our instruments, but a gap in the physical record itself. A place where the information simply does not exist in any form that could, even in principle, reach us. The distinction matters. It matters the way the distinction between a locked door and a wall matters. Light travels at approximately 300,000 kilometers per second. This is the fastest anything, any signal, any information, any causal influence can travel through space. It is not a technological limit. It is not a limit we will engineer around. It is a structural feature of space-time itself, embedded in the geometry of special relativity, holding everywhere in the universe at all times. Nothing outruns it. This means that what we can observe is bounded. The universe has been expanding for 13.8 billion years. Light emitted at the moment of the Big Bang, or as close to that moment as light could travel freely, has been travelling toward us ever since. The sphere defined by how far that light has travelled is our observable universe. Beyond that sphere, things exist. The universe almost certainly extends far beyond what we can see, but their light has not yet reached us. They are, for now and for the foreseeable future, invisible. That boundary is already a limit. Not a wall in space, but a wall in time. A horizon defined by the finite age of the universe and the finite speed of light. But it is not the deepest limit, not the one this chapter is about. The deeper limit sits at a specific moment in the universe's history, approximately 380,000 years after the Big Bang, when the temperature dropped low enough for electrons to bind to protons and form neutral hydrogen. Before that moment, the universe was a plasma, ionized, opaque, a dense fog of charged particles that absorbed and re-emitted photons almost instantly. Light could not travel freely through it. Any photon generated in the early universe was immediately scattered, absorbed, redirected. There was no transparency. At 380,000 years, the fog cleared. Atoms formed. The universe became transparent. The photons that were traveling at that moment, the photons that had been scattering endlessly through the plasma, were suddenly free. They streamed outward in all directions. They've been traveling ever since. We detect them today as the cosmic microwave background, redshifted by the universe's expansion from visible light down to microwave frequencies arriving at our detectors from every direction in the sky with almost perfect uniformity. The CMB is the oldest light we will ever detect, not the oldest light that exists. There is no older light. Before 380,000 years, there was no free light. The photons that existed were trapped, scattered, thermalized. They carry no directional information, no image of what produced them, no signal from any specific structure or event in the early universe. Everything before 380,000 years is, tussen electromagnetic net of Beethoven, permanently invisible. There are ways around light. Neutrinos, for instance, barely interact with matter. They streamed freely through the plasma of the early universe from about 1 second after the Big Bang. A cosmic neutrino background, analogous to the CMB, but made of neutrinos and originating from a much earlier time, should exist, permeating the universe in every direction. We have strong indirect evidence for it. The predictions it generates about the early universe match what we observe, but we have not directly detected it. Neutrinos interact so weakly that detecting the low-energy neutrinos of the cosmic background requires detectors we do not yet have. Gravitational waves are even more penetrating. They interact with matter so weakly that they pass through everything essentially unimpeded. A primordial gravitational wave background, generated during inflation, or during a bounce, or during whatever process occurred in the universe's first moments, would carry information from the earliest fractions of a second. Detecting it would be, in a real sense, hearing the universe before the CMB wall. This is a genuine scientific possibility, not guaranteed, not imminent, but possible. Experiments like LISA, the proposed space-based gravitational wave observatory, and pulsar timing arrays might eventually detect signatures of primordial gravitational waves. What those signatures look like would distinguish between different models of the early universe, between inflation in various forms, between bouncing cosmologies, between the CPT symmetric model, and others. So the CMB wall is not the absolute limit of everything. It is the absolute limit of electromagnetic observation. The Planck wall is different. At the Planck time, 10 to the negative 43 seconds, all known physics stops working. Not because the universe was doing nothing interesting, because the energy scales and density scales at that moment are so extreme that quantum gravitational effects dominate completely, and we do not have a complete theory of quantum gravity. Whatever was happening at the Planck time, whatever geometry, whatever field configuration, whatever process was operating, generated no signal that our current theoretical frameworks can cleanly describe or predict. Even if we could detect gravitational waves from the earliest moments of inflation, those waves originated after the Planck time. The Planck epoch itself, that first 10 to the negative 43 seconds, is, with our current physics, a closed book. Not because the information isn't there, because we don't have the language to read it. This might be temporary. A completed theory of quantum gravity, loop quantum gravity fully developed, or string theory with its cosmological predictions worked out, or something we haven't built yet, might give us the tools to reconstruct what happened at Planck scales from indirect evidence in later observations, the way a geologist reads ancient climate from ice cores, not observing the past directly, but inferring it from what the past left behind. Might. The word is doing real work there. Here is what we cannot know with any instrument currently conceived or any theory currently in hand. What, if anything, preceded the Planck epoch? What the specific geometry of the universe was at the Planck time? Whether the bounce of loop quantum cosmology actually occurred, and if so, what the prior contracting universe looked like? Whether the no-boundary proposal's imaginary time geometry corresponds to something physically real or is a mathematical device. Whether the CPT symmetric anti-universe exists. Whether the universe tunneled from nothing or from something. Whether inflation happened in the form we model it, or in some other form, or not at all, and something else produced the same observational signatures. None of these questions has a currently available answer. Some may never have one. There is a specific kind of honesty required here that science, at its best, practices, and that popular science often does not. The honesty of saying this question may be permanently beyond reach, not because we are not clever enough, not because we haven't tried, but because the physical record, the causal structure of the universe, the opacity of the early plasma, the breakdown of known physics at the Planck scale, has built walls into the architecture of what can be known. Walls that are not made of ignorance. I find this, and I recognize this might be a strange thing to say, almost restful. Not in a defeated way. In the way that knowing the actual shape of a problem is restful compared to not knowing whether the problem has a shape at all. The limits are real. They are specific, they are not moving targets, and within those limits, there is still an enormous amount of space to work in. Enormous and active and genuinely uncertain. There is a letter somewhere. This is the only way I can think to put it, and I recognize it's an imperfect way. A letter written before the universe was transparent. It exists. The physical processes that produced the early universe wrote it. The information is in there, encoded in whatever the pre-CMB universe was doing, in the geometry of the Planck epoch, in whatever came before or instead of a singularity. We will never open it. Not because it was sealed maliciously, because the envelope is made of physics. The opacity of the early plasma, the breakdown of space-time descriptions at Planck scales, the one-way causal structure of an expanding universe, these are the envelope, and they do not open. What we have instead is what leaked through. The CMB, with its precise temperature fluctuations, the abundance of light elements, which remember the first 3 minutes of nucleosynthesis, the large-scale structure of galaxies, which remembers the acoustic oscillations of the early plasma, the Hubble constant imperfectly measured, pointing at something about the early expansion rate that we haven't fully resolved. These are not nothing, they are extraordinary. A century ago we didn't know the universe was expanding at all. Now we are debating the precise rate of that expansion at different epochs, using instruments that measure temperature differences of millionths of a degree across the entire sky. But they are not the letter. They are the postmark, the faint impression on the outside of the envelope, the weight of it in your hand, telling you something is inside, something was written, something happened, without ever telling you what. The universe began, or transitioned, or tunneled, or bounced, or emerged from a geometry without time. Something happened 13.8 billion years ago that we are still inside of, still moving through, still made of, and some part of it, the most intimate part, the moment itself, we will simply never see directly. That's not a failure. It's just where the light runs out. Go outside if you can, or find a window that faces somewhere dark enough that the glass doesn't just give you back your own reflection. It's probably cold. Late nights usually are, even in seasons that don't feel the cold during the day. There's a specific drop that happens after midnight when the ground has finished releasing the heat it absorbed and the air settles into something quieter and more honest. The cold is fine, it's part of this look up. Not at anything in particular, not hunting for a constellation or tracking a satellite crossing the field of view, just the sky. The whole field of it. Let your eyes adjust, which takes longer than people expect. 10 or 15 minutes before the dim stars start separating from the background dark, before the sky stops being a flat black surface and starts having depth. There are more stars than there were a moment ago, and more than that a moment later, as the rods in your eyes gradually come online. What you're looking at is old, all of it. The light from even the nearest stars left them years ago. The light from the faint smear that is the Andromeda galaxy left it 2.5 million years ago, before our species existed in any recognizable form. The light from more distant objects, the faint galaxies at the edge of what naked eyes can detect, left them tens of millions of years ago. You're not looking at the sky as it is, you're looking at the sky as it was, a layered collection of different pasts arriving simultaneously at your retina. None of it knows you're watching. This is worth sitting with. Not philosophically, just physically. The light from Andromeda has been travelling for 2.5 million years. It crossed an intergalactic void, 2.5 million light-years of expanding space, and tonight some small fraction of those photons happened to enter your eye. The galaxy did not aim them at you. The universe did not arrange for this particular meeting. The photons were travelling in every direction simultaneously, a sphere of light expanding outward from each point of emission, and your eye intercepted an infinitesimally thin slice of that sphere by virtue of being in a particular location on a particular night. There is no significance to this meeting from the photon's perspective, because photons don't have perspectives. There is no record kept. The photons that missed your eye by a millimeter travelled onward. Will travel onward for billions of years until they're absorbed by something else, or redshifted into frequencies too low to interact with anything. The universe doesn't notice the looking, and yet here you are, something that emerged from the same Big Bang that produced those photons, assembled from the same nucleosynthesis that built the carbon in Andromeda's stars, looking at the light and, unlike the light, knowing what it is. That asymmetry is real. It's not poetic license. The universe produced things that can ask questions about the universe. Whether that means anything, whether there's significance embedded in it, or whether it's a brute fact without implication, is not a physics question. But the fact itself is solid. Everything we covered tonight, the singularity that was never a thing, the shuttlecock geometry of the imaginary time, the bounce at the Planck density, the entropy problem that corners cyclic cosmologies, the theorem that said even inflation had to start, the antimatter mirror on the other side of the bang, the tunneling from nothing, the permanent opacity of the early universe. None of it is visible in the sky. The sky doesn't carry labels. Andromeda doesn't announce that it's 2.5 million years old and made mostly of dark matter, and heading toward the Milky Way at 110 kilometers per second. The photons don't mention that they are the tail end of a process that began in nuclear fusion at temperatures of millions of degrees. The sky is just the sky. It has always been just the sky, to every human who has ever looked at it. The shepherds and the sailors and the people who built structures aligned with solstices, and the children lying on their backs in fields, they all saw what you're seeing now. The same stars, more or less, the same darkness between them, the same faint sense that there is a lot of it, and that being under it does something to the scale at which you experience yourself. What has changed is not the sky. What has changed is what we carry when we look at it. We carry now the knowledge that the universe is 13.8 billion years old and that this age is a measured quantity, arrived at by multiple independent methods, not a guess. We carry the knowledge that the expansion is accelerating, that the universe is not heading toward a big crunch, but toward a slow, cold dispersal over trillions of years. We carry the knowledge that the Big Bang was not an explosion in space, but an expansion of space, that the singularity is a breakdown of our equations and not necessarily a description of a real moment. That several serious and mathematically developed frameworks suggest the question, what was before the Big Bang, may be either unanswerable in principle, or dissolved by the geometry of an imaginary time, or answered by a prior contracting phase, or answered by a tunneling event from the literal absence of space-time. We carry the knowledge that we don't know which of these, if any, is correct, that the Planck epoch is permanently opaque to electromagnetic observation, that the CMB is the oldest light we will ever detect, and that everything before it is written in a language, primordial gravitational waves, neutrino backgrounds, quantum gravitational signatures, that we are only beginning to learn to read. This knowledge doesn't make the sky larger. The sky was always exactly this large. It makes us, or it can make us if we let it, more accurately small, not diminished, just accurately scaled. There is a difference. The question we started with, the one a child asks and then sets down, and then picks back up again decades later at 2 a.m, hasn't been answered tonight. Not fully, maybe not even mostly. What's happened instead is that the question has been mapped. Its shape is clearer now. Its edges are more defined. We know where the frameworks agree and where they diverge. We know where the permanent limits sit. We know which doors are locked and which are merely closed. That is not nothing. It is actually an extraordinary amount when you consider that a century ago we didn't know galaxies existed beyond the Milky Way, didn't know the universe was expanding, didn't know about the CMB or inflation or the Planck scale or quantum cosmology or any of the frameworks we've spent tonight with. The question has been with us in some form since humans first had the cognitive architecture to ask it. The answers, partial, contested, provisional, genuinely strange, have mostly accumulated in the last 100 years. Somebody is still working on this, right now, tonight, in offices and at telescopes and at desks covered in papers. People are genuinely trying to understand what happened at the beginning of everything. Writing code that processes CMB data, developing the mathematics of loop quantum gravity, running numerical simulations of bouncing cosmologies, testing CPT, symmetric predictions against observational constraints. The work is ongoing. It will be ongoing for a long time. The sky doesn't know any of this either. It is indifferent to whether we figure it out. The photons will keep arriving regardless, but you know it, or some of it. Enough of it to look up and feel the weight of the question differently than you did before. Not heavier exactly, more specific, more grounded in what is actually known versus what is assumed, versus what may be permanently beyond reach. That feels like something worth having. The cold is still there. The stars are still there. Andromeda is still crossing the sky at 110 kilometers per second, closing the distance between itself and this galaxy in a collision that won't happen for another 4 billion years, and that when it does, will produce not the catastrophic destruction the word collision suggests, but a slow gravitational dance. Two sets of widely spaced stars passing largely through each other. The night sky rearranging itself over millions of years into new shapes that no one alive now will see. Everything is moving. Everything has always been moving. The expansion is still happening right now in the space between every object too far apart for gravity to hold together. The universe is still, in the most literal sense, not finished. Neither is the question, go back inside whenever you're ready, or stay out a little longer if the cold is bearable and the sky is clear. There's no reason to rush. This project is self-funded and made with no backing, no production team, and no budget beyond what comes from people who find it worth supporting. If these hours of slow, careful physics have meant something to you, if they have made the dark feel more interesting rather than more empty, there's a Patreon linked in the description. It keeps this going. It funds the research, the time, the quiet work of trying to explain the universe without rushing it. Join if it feels right. No obligation genuinely, but it matters more than I usually say out loud.